Well, thank you very much, Peter and Stein Erik, for inviting us to talk here at this SAM conference. I have been very much looking forward to come here and give this talk in this nice place up in the almost northern part of Sweden. The thing we present here is sort of based on many years of working on an object-oriented programming language called Beta, together with Kristen Nygaard, who did Simula, as most of you may know, and my colleague Bent Brun Christensen from Aalborg, and then my co-author here, Birger Møller-Pedersen. Actually, it would have been better if Birger was here, because he was actually part of the development of object-oriented SDL back in the late 80s. We had a big Nordic project called Møller, where Birger worked on object-oriented SDL, and I mainly worked on developing compilers and other things for Beta. And Birger was also involved in the development of UML 2.0. My own knowledge of SDL is very limited, so I'm sort of thin ice here. I followed the work of Birger in developing object-oriented SDL, but Birger was unfortunately not able to participate. There's a lot of documentation about what we've been doing in Beta. There's a book, you can download it from my webpage. It's out of order right now. And it's also so old that we were invited to present it at the History of Programming Languages conference back in 2007. It's very, very strange to be so old that you present things at a history conference. And now it's 15 years ago or something like that. If you look at object-oriented programming, it has been around for more than 50 years, tracing back to Simula in the 60s. And it's clearly the most dominating style of programming these days. A lot of applications have been made, and object-oriented modeling sort of replaced what we were used to in the 70s and 80s on structured analysis and structured design. And most of you are so young that you probably never heard about these things. But we were struggling with SAND-SD in the 70s, and object-oriented modeling was really a good step forward here. This one. Then when the object-oriented modeling started to emerge with people like Slayer-Mello, Rombauer, Booch, and others, it was really a good thing in the sense that it replaced structured analysis and structured design. But the unfortunate effect of it was that the object-oriented community was sort of split into two more or less disjoint communities. There were on one side the programming people working on programming languages, and not very much concerned about modeling. And on the other side, we had the modeling people that eventually ended up with UML, very much focusing on modeling with very little attention to programming. So it was sort of two disjoint communities that was more and more going in different directions. And if you go back and look at how it all started with Simula, the Simula was actually developed to be a language for programming as well as modeling. They called it system description at that time. The name Simula indicates that it was a language for simulating real-world systems. And if you're going to simulate real systems, you need to create models of these kind of systems. So Simula was actually developed to be able to describe models and at the same time program these models on a computer. And if you look at the introduction of the first paper on Simula, it clearly states that it was a language for describing systems. That's the term they used for modeling and for programming such systems. So the original idea with object-oriented programming was that it was programming as well as modeling. And usually when we teach programming, we teach it as modeling. So for us, programming is really modeling. There's no way to have these as separate things. Yes. And if you go back and read some of the old papers about object-oriented programming, there's a lot of people that clearly states that a good thing about object-oriented programming is that compared to old-fashioned imperative programming, it was a good way of sort of creating programs that reflects the domains of what you were actually programming. And Cott and Jordan, if you remember that, one of the first books on object-oriented analysis said it in the way that it's sort of kind of concepts that you learned in kindergarten you used when you define your object-oriented models. If you look at mainstream object-oriented programming, and then you will see that most people consider the main advantage of object-oriented programming to be reuse of code. Of course, when you make a subclass and inherit from some superclass, you inherit the code there, you can modify your virtuals. And if you find a class somewhere that sort of do whatever you want to do, but with a few changes, you may inherit from it, redefine things, and then whatever, your job is easier. But this leads to a lot of spaghetti-like code where you have class hierarchies that are made from reuse point of view, sort of a modeling point of view. And if you read textbooks about object-oriented programming, you hardly see anything about modeling. Smalltalk, which is a fantastic system, if you read the books about Smalltalk, you see nothing, or very little at least, about modeling. It's mainly something for programming and reusing code. And if you look at some of the very early papers about object-oriented programming, Peter Wegner and Stan Sedonic, some very, very brave people, they present inheritance as an incremental modification technique, nothing about modeling. And other people like William Cook states things like objects, the philosophical viewpoint that objects model the real world has never appealed to me. So for him, objects is something with a special version of lambda calculus, which is not very useful when you're doing modeling. And you can go on in this way. And you want a lot of people talking about reuse as this is what the advantage you get from object-oriented programming. So we think it's a real wrong direction, because the real good thing about object-oriented programming was that you could create programs that in a better way reflect sort of the world or the domain that you were actually programming. And Birger and I wrote a paper about that, which we presented at the Splash Onward conference in New Zealand last year in December. We tried to argue that modeling should come back and be the real center of object-oriented programming instead of reuse. Reuse is okay, but it's sort of a side effect of modeling. Then how about object-oriented modeling? There's a red dot here. As I said, the modeling community has, of course, focused on models and modeling, and more or less independent of programs and programming. There has been attempts like executable UML, etc., but it's far, far away from what you can express in real programming languages. And there has been a lot of focusing on notation and semantics of diagrams. And what we think is lacking is sort of an underlying conceptual framework. And by that, we mean what is really the semantic basis on things like UML, syntax and diagrams is fine, but what is the underlying semantics here? Now, either Einstein and Niels Bohr said you had to exaggerate in order to argument, so maybe it's a bit exaggerated, but this is really how we see it. Programming languages do little about modeling, and modelers, on the other hand, do very little about programming. We should unite these things. So our point of view is that you need a conceptual framework for object-oriented modeling. And this conceptual framework is, of course, also need for programming if you have the standpoint that programming is also modeling. And if you have a conceptual framework, it has implications. First of all, programming and modeling communities should try and join forces instead of splitting. And it also has implications for designing your languages. And one thing, I'm not a big fan of UML, but one of the nice things about UML is that they have language elements for describing snapshots of program executions. It's defined what a snapshot of an object looks like in an object diagram. You can create sequence diagrams describing snapshots of program executions, which is very nice. And no programming languages actually consider doing the same thing. For this beta language, or a variant of the beta language, we have defined a notation which is a combination of object diagrams and sequence diagrams, and our debugger actually generates these diagrams. So it's sort of at the same level as if you would do a design. For beta, we actually developed a conceptual framework as part of the development of the language. And this, for us, included a definition of what did we actually consider to be an object-oriented model. How do you understand phenomena and concepts from your application domain? And what about conceptual means such as classification, composition, context, etc., etc.? And we think that this conceptual framework could be a starting point also for designing a conceptual framework for modeling and programming in general. And as I said before, we sort of consider this to be a semantic foundation, similar to if you do functional programming, you have mathematics as your semantic foundation. Here we think that this is more well-suited for object-oriented programming and modeling. So the first thing is here, what is really a model? And if you look at, oh, I thought it was over time already.
Excited audience.
What is really a model? Webster defines a model to be a small or large abstract or actual representation of a planned or existing entity or system from a particular viewpoint. And if you take one of these elements one by one, then if you make an abstract model, it's typically in terms of a mathematical description, like Newton's laws of motion. If you make an actual modeling, it's typically you build something like a structure of molecules, as shown here, representing some part of the system. So you can either do it in an abstract way or in an actual physical way. And for object-oriented programming, the interesting thing is, of course, this is an abstract model we make or an actual physical model. You also do models for either planned or existing systems. Architects build models of things they are planning to build in the future. Whereas, for instance, physicists or others, they build models of existing things like the solar system. In programming, you have the same thing. You may model some existing system, or you may create a model of something you imagine to build for the future. And then a very important thing is that your model is built from a particular viewpoint. A map, for instance, here is a model of a city. And there's a quite difference between what are you actually using this model for. Is it a model of Oslo streets, or is it a model of the trains and trucks within Oslo? You end up with two different models. And sometimes it's necessary to tell students and young people you cannot create a model that has everything in it. You have to sort of find out what is really the purpose about it. If you go back in the a couple of 100 years ago, there were actually people who tried to make a complete map of the city of New York at that time, but they then realized that this was not possible. The only complete map of New York City is New York City itself. So this thing about perspective or viewpoint is very important. For object-oriented programming, we define the program execution to be the model. And program execution, as the words say, this is the dynamic system of objects that is generated during execution of the program. So this is what we think of as a physical model, and what Webster called actual model. So you actually think of the objects as building material where you build a physical or actual model of your system. And this, as I said, may be an existing, maybe of an existing system or something we plan to develop in the future. And of course, it has this thing from a particular point of view. And if you look at this picture here, if you have some vehicles, cars, buses, and trucks, you may build a model in terms of the objects being the program execution that actually represents the vehicles of your system. And the program is a description of this model. And why am I saying this? This is because if you look at UML, for instance, it's the diagram, which is like the program that they consider to be the model, which we don't think is a very useful thing. If you look at other ways of building physical models here, for instance, you have this domain of cars, and you have a description here from Lego on how to build a model. And the model is the physical car here. I don't think anybody would think that the description of how to build the car is actually the model. It's the toy car built from Lego bricks, that's the model. So in our world, the analogy is that the Lego bricks and objects are the building material, and the toy car and the program execution is the model. And the program is then just the, say, description of the model. This may be a subtle, but we think very important difference in how you actually look at models. You are welcome to interrupt me if you strongly disagree. Next thing, the real world consists of a lot of phenomena, and you form concepts to organize and understand these phenomena. So how do you go ahead with that in your object-oriented models? And the thing we ended up with is that a phenomenon is something that exists in reality or in the mind of people. And you may have physical phenomenon like the cars, vehicles, and other things which consist of some kind of physical material that you want to represent by objects. And these physical things like cars, they may have properties like the weight, license number, etc., which are other kinds of phenomena. And finally, they may also perform transformations that sort of change the state of the physical objects or the properties of these objects. So we think it's very good to have a clear understanding of what is a phenomenon, what kind of phenomena is there in the real world, and how do you actually represent them in your programs. Similarly, what is really a concept? A concept is sort of this form of generalized idea that makes it possible for us sort of to comprehend and organize and understand the real world. So we don't have to deal with all possible cars. We can talk about the concept of a car, etc., etc. And in general, there are many types of concepts sort of associated with vehicles. There are buses, cars, ambulances, trucks. There are properties like curb weight, trip, vehicle register, registration, which are also, again, other kinds of concepts. The traditional way of understanding concepts is that it has an associated thing called the extension of the concept. The extension is sort of all the members of covered by this concept. And these two cars here, the Donald Duck cars and the Grand May Ducks electric car, this is actually the world's first electric car, built back in the 30s, used by this, what is he called in English? Bestemorand. Yeah, something like that. These drawings were actually made by Birger's granddaughter. We couldn't get permission from Disney to print some of the Disney ones. At least we applied for it, but they didn't answer. We didn't hear from them until the deadline. So we didn't want any trouble with the publishers here. So in addition to the extension, there's something called the intention of a concept. This is sort of the properties of the phenomena covered by the concepts. And the properties here for vehicles is things like curb weight, color, number, wheels, engine type, etc., etc. And the designation of a concept is sort of the collection of names or pictures by which this sort of concept is known. This formulation of a concept goes all the way back to Aristotle. If you look at more modern philosophers, some of them formulated in another way. There's something called prototypical concepts, not to be confused with prototype-based programming, etc., etc. But if you look at what you can represent in a programming language nowadays easily, it's sort of still the old-fashioned Aristotelian kind of concepts, where more modern views of concepts is not that easy to represent directly. And one of the reasons for the conceptual framework is that it sort of should be broader than what you have in your programming language. Because when you model with a programming language or modeling language, this one put restrictions on what you can describe. And you have to be aware of these kind of descriptions. If you're an old-fashioned COBOL programmer, you understand the world as a COBOL program. If you use Java, you may understand it as a Java programming, but it's still limited what you can actually describe. We also think that it's a lot of examples where you only have one kind of a phenomenon. And in one of the examples, we have this Goldfinger Aston Martin equipped with guns and ejector seats and oil slickers, etc., etc. And since there's only one instance of it, you should be able to describe that here's just this one car. You can do it in some languages, but in most languages, you have to create a class and create instances. This is a small thing, but anyway, we think it's important. If you consider sort of conceptual means for understanding and organized knowledge, in general, there is this thing about classification. How do you organize phenomena and concepts in hierarchies? There's this thing of composition. How do you understand the structure of physical objects as parts and wholes? And then finally, this thing which we have chosen to name context. How do we understand the context of phenomena and concepts? It's not something that is very common in most languages, but I'll return to it. I think we all know about hierarchical classification, that you can organize your phenomena and concepts in a tree-structured hierarchy. So here you have vehicle and you have specializations of this general concepts, which is again a generalization. And we then have the phenomena here being all the vehicles. And again, you have the extension here of the concepts, which are all the vehicles here. And you have bus here, which has only a subset of the extension of vehicle up here. So the extension of a specialized concept is sort of a subset of the extension of the generalization. And the intention is an extension of the intention of the superclass. We often use this because many people are confused about this thing about subclass, etc. But if you look at the extension, it's quite clear that the extension of a subclass is a subset. So subclass gives meaning if you talk about the extension. If you look about the keyword extend in Java, it's sort of related to the intention because you extend the intention. And we think that it's useful that students and others sort of are aware of these kind of subtle details. If you read about the book by Bjarne on C++, he clearly states that this was one of the confusing things for him in Simula. So he invented this thing about derived and base class in C++. Otherwise, he really did a good job. We were in the same class at Aarhus University 55 years ago, something like that. If you look at things like multiple inheritance and classification, then most proposal for these things called multiple inheritance, mix-ins and trails are primarily used for code reuse. And they add a lot of complexity and ambiguity compared to single inheritance. And there's very, very little about modeling if you read about these concepts. Again, we think that if you have a proper conceptual framework, you may actually teach students about different situations about classification. Because of course there are non-tree structured classifications of objects, where you here have geometric figures, and you have concepts like romb and rectangle, which have overlapping extensions here, because these squares are rectangles, but they are also rhombs. So this is a good example of non-tree structured classification hierarchy where you have overlapping extensions. And if you want to represent that, you of course need something like multiple inheritance. But there are other examples where people use multiple inheritance. Most often when you have independent tree-structured classifications of the same objects. Here you have some people, and you may classify them according to their profession, which gives you one hierarchy here. You may also classify them according to their nationality, which give another classification of the same objects. But no mainstream programming language is sort of able to represent this in a reasonable way. And this is why you often see in some kinds of programming, then you see things like a subclass called American Nurse, which combines both of these. You see an Asian teacher, an Asian nurse, etc., etc. And it ends up in a big tangled, unstructured hierarchy. And one reason for having, as I said, this conceptual framework is that you should be able to tell the students that there are some limitations of your languages. If you have this situation, you have to get around it in some way, but be explicit about that you do not represent it directly. You have some way of getting around it in your programming language. Another example is dynamic classification. You may have objects that change class membership during their existence. You have Lisa Larsen here. She may start as a student in computer science. And then when she graduates, she becomes a programmer. And when she reaches a certain age, like most of us, she's not able to program anymore, then she becomes a manager. Are you managers, any of you? No languages are very good at representing this kind of structure, but if you have sort of long-lived applications, you will need to get around with it in some way. In Smalltalk and some languages, you may actually change the class pointer, which is sort of a dubious way of actually doing it, but it may work. Composition is sort of reasonably well known because you know it from most languages, but of course composition should be handled in just the same way as classification, because both are very important means. You may describe things as parts. A vehicle may have wheels as parts. It may also have references to other objects like its owner. Value composition is well known, where a date is a composition of some numbers. And for methods, procedures, or functions, or whatever, you are used to a method calling other methods. But this is sort of pretty forward standard. The next thing I will mention is the thing we call context. It's really about nesting of classes and what was used to call block structure in Algol 60. In Algol 60, you can nest procedures to an arbitrary depth. And the same you can do in Simula with classes. And we can do it in beta. Java sort of added this thing of inner classes, which is similar to class nesting in Simula, but it has some limitations which are very, very odd, and it's very strange they were not able to sort of fix that in Java. C++ and C# may have nesting of classes, but you are not allowed to access global variables in the enclosing objects, which is again a funny kind of restriction. I'll give you an example of how we consider this. If you look at an airline company, it may have a timetable with all its routes. And for each route, there is an entry in the timetable, and in a route may be represented sort of by an object. So here you have the routes, which is Scandinavian Airlines. This thing here, one way, Aarhus. Well, some problems with the colors on this one. I don't know, but the colors are not right. But these are entries in this timetable. This is the one way from Aarhus to Stockholm or Oslo, and the other way back. And this one sets the time of the date to leave, and it goes sort of every day in the year. In a similar way that for a given route, it may take place every day of the year. So the actual flights of a given route may be represented by an object of class flight. So for each entry in the timetable, you may have several instances of when this route is actually taking place. Sorry, there's problems here with I don't know what kind of different kinds of computers. So you have routes and you have flights. And how do we represent this? We actually, we have a class routes that represents sort of the routes SK 1926 from Aarhus to Oslo, and a similar one from Oslo to Aarhus. And then we have a class here representing the actual flights. This is for this route here, there's a flight instance for every day. And for this route here, there's also a flight instance for every day. And the way we simply do this in a program is that you have the class root here with the general information. Where does it come from? Where does it go to? What is the departure time? What is the flight time? And then there is a class flight nested in root here saying, what is the departure date? What is the actual departure time? And what is the actual flight time? And some method here for computing the delay and some other stuff here. So class flight here naturally belongs to the context of a root object. And when you compute, say, sort of the departure delay, you refer to the departure time in the enclosing root object. And you subtract it from the actual departure time of the actual flight taking place. And this then gives you sort of the delay. And so there's a lot of examples of where it's very, very useful to encapsulate classes within other classes. You're used to encapsulate methods in classes and objects. As you belong there, it's quite the same thing for classes, in our opinion. I think I skip these two. Yeah. The next thing is about modeling concurrent processes. As stated there, it was quite essential for Simula to be able to model processes as well as objects with data and methods in it. They clearly stated that they needed subclasses for data structure and processes, and they needed it for processes and not only just for pure data records. And in general, we don't think object-oriented programming languages are very good at representing concurrent activities or parallel activities. We are a little sort of, where is really UML with respect to that? I'm sure SDL is better. I said the right thing here. But
5 minutes?
5 minutes, yes, very good. But one thing we also think is important is that you should also consider classification of activities, just as you have classification of data objects, and your languages to support that. If you look at a clerk in a travel agency, he or she may perform various tasks. They may update web pages, they may do booking services, they may do invoicing. And for booking services, they may make a car booking, a flight booking, or hotel booking. And these are may then also be organized in a hierarchy similar to a class hierarchy. So in Simula and Beta, you may actually describe the structure of hierarchical processes also. And in Beta, we actually have it also for methods. So you may describe a method that inherits from another method, which is very useful in some kind of situations, but I don't really have time for that. Another thing that we think should be considered, and we don't mention it in the paper, but that is to sort of be quite clear about the distinction between objects and values. There is a very, very good paper back in the early 80s by Lehrmann, where he quite clearly discussed the differences between objects and values. And I don't have much time to go into it here, but objects have identity and exist in times and space, but values are sort of timeless concepts. And this should be reflected in your programming language. And if you look at units, no programming language really support units very well. In the new language we do on Beta, we can represent things like a dimension, like mass, electric current, time, magnetic flux density, etc. And then use the various units here. So when you declare this variable as kilogram unit as a mass dot kilogram, it means that it's in the dimension mass of type of unit kilogram. And the really important thing here is that there's no overhead compared to doing real flows. So the compiler is able to verify that the dimensions of this expressions like this are really consistent. And I think from a modeling point of view, it's very important that you're also able to do that. One of the implications of the conceptual framework for beta was that we wanted to be able to just represent the concept in general. So we ended up with this thing called a pattern. And a pattern is actually a generalization of class, method, function, data type, process type, or whatever you have in your programming language. And the good thing about that is that classes, in order to have subclasses, a pattern also may have sub-method, a sub-method here, and this works for methods, functions, data type, processes. Virtual methods implies that we have virtual patterns, which means that we actually also have virtual classes, etc. And we have patterns as first-class variables, which means that classes, methods, etc. are first-class values. And the same thing about nesting. And if you look at this thing about reuse of subclasses, the idea was really that a subclass in Simula should be behavioral compatible with a superclass. But if you're only considering reuse, you don't get that. But clearly, also for programming in general, it's very hard to guarantee behavioral compatibility. But since I'm running out of time, I'll not talk very much about that. Maybe some questions here at last on language impacts. UML has this idea about classifiers, which to sort of resemble beta patterns, but we don't really know what about it. The final thing one of the final things I will mention, I said we had this people generating sequence diagrams. So this is a snapshot from the program executions, where you see the objects and you see the method invocations here, and you can inspect them. And this is some nice thing we learned from UML. I think I said that you don't have to use UML for real modeling. You can model in your programming language. And the final slide, I'm on time now. For beta, we actually designed a textual syntax, but also a graphical syntax. And the compiler produces an abstract syntax tree here. And if you make changes to the text, it updates the diagrams. If you make changes to the diagrams, it updates the text. The reason is that in practice, we never see any projects where you first start out by doing some modeling in terms of UML, then you generate some code, and then that's it, because you want to change the code. In most projects we know about, people do iterative development and do prototypes, and they change the code, and the diagrams are left behind. But with this kind of tool, you can alternate freely between changing the code and changing the diagram. Yes, I can stop here, Mr. Chairman.